Welcome back. We will now have a pre-recorded talk on oneAPI project updates. Rod will discuss a summary of changes on the open source implementations of the oneAPI spec. Over to you, Rod.
Hello, I am Rod Guisen, lead architect of oneDNN at Intel. Today, I will give a brief overview of the oneDNN project, updates on main improvements that were made in the past 12 months, and I will share future plans for the project. oneDNN is an open source and cross-platform library that helps developers create high-performance deep learning framework. We achieve that by efficiently abstracting hardware architecture details and performance optimization complexity. It is integrated and enabled by default in most popular frameworks such as PyTorch, TensorFlow, and Paddle. oneDNN is open source, with its code available on GitHub, and we welcome contributions. Multiple companies are already contributing to the project, with Intel, ARM, Fujitsu, and Codeplay being the main contributor. oneDNN is also available in binary form on major Linux distributions native packages maintained by the Debian Science. You can find more about oneDNN on the GitHub page, and you can reach the development team on the project Slack channel or through GitHub issues. In the past 12 months, oneDNN development focused on 3 areas. We introduced new low accuracy data types, namely signed and unsigned info, 2 flavors of 8-bit floating point that were standardized by the Open Compute project, and double precision floating point. We also added API extensions and optimizations for new numerical recipe and numerical mode. Weights-only quantization, where quantized inputs are up-converted upon computation, accumulation mode to allow more speedups on some platforms, deterministic mode for run-to-run reproducible results, and stochastic rounding to help with low precision training. We continued optimizing emerging AI patterns through Graph API, with optimizations for popular attention patterns such as scale.product attention, multi-query attention, grouped query attention, and smooth quant. We also extended oneDNN to new usage models by introducing microkernel APIs, which allow users to compose single-thread building blocks and efficiently prototype custom numerical recipes and compute patterns on CPU. We expanded sparse API with COO and structured sparse formats, and we introduced capabilities to serialize and deserialize primitives and memory descriptors, which are currently in use in Torch IoT Inductor. Finally, we continued to open up public development of oneDNN by exposing generic GPU configuration, which allows any device with a SYCL compiler and a SYCL runtime to run oneDNN, thanks to a new set of portable SYCL kernels. We extended code owner list with contributors from AWS, ARM, and Codeplay. And finally, we now have AR64 public CI available. The future plans for the next year on API sides are to continue support of emerging computing patterns and data types, in particular those proposed by the Open Compute project like microscaling data types. We plan to promote sparse APIs as stable, since they are now used in external projects. We will also continue to improve dynamic shapes handling and performance. And finally, we will continue to refine the microkernel API as it gets adoption. On the ecosystem side, we are moving our main development vehicle from private repository to public repository, which will allow each backend to be independent of the core team. Finally, we would like to increase public CI to more platforms and configurations. If you're interested in contributing to oneDNN, we can use your help on 3 different aspects. First, API discussions and definitions are public through RFCs on GitHub, so you are welcome to open such an RFC and start a discussion on new API extensions, as well as comment on existing ones. The UXL AI Special Interest Group also hosts meetings and a mailing list, and you are welcome to drop suggestions there and share relevant experience. Second, oneDNN development is open source, and multiple companies are actively participating to oneDNN development. You can participate in oneDNN development too by picking an issue with the Help Wanted tag on GitHub. Those are good candidates to start contributing to the project. You can also add support for a new platform or add optimizations to an already supported platform. Note that the oneDNN developers and maintainers are reachable on oneDNN Slack channel and GitHub issues if any help or guidance is needed. Finally, on the infrastructure side, we are also looking for contributors for OpenPower, IBM Z, RISC-V, and LongArch64 platforms, as well as CI runners to expand validation scope to more platforms. Thank you, and we hope to see you soon contributing or using the oneDNN project.
This is a presentation on oneAPI data analytics library, and my name is Nikolai Petrov. I'm engineering manager of the OneDAL team. This is architectural review of the OneDAL and scikit-learn Intel extension. OneDAL library itself implements C++ interfaces and supports different algorithms within the classical machine learning domain in the batch, streaming, and distributed modes, implementing both CPU and GPU computations. OneDAL itself also utilizes the other libraries such as OneTBB and OneMKL for threading and math operations on the matrices primarily. And on top, it enables scikit-learn Intel extension, which is Python APIs that are compatible with the scikit-learn and can accelerate it. There are certain libraries and products that can use scikit-learn Intel extension or oneDAL directly, and those oneDAL accelerations enable those products upstream. Also, there is possibility to take existing XGBoost, CutBoost, LightGBM pre-trained models, convert them to oneDAL format, and run faster inference. What makes oneDAL faster? First one is it's using oneMKL library to run on Intel, and there is open source, OpenBLAS support integrated as well. The second thing is we implement threading utilizing different cores on the system. Unlike stock scikit-learn, their threaded algorithms shows noticeable performance improvements comparing to the stock scikit. oneDAL use vector instructions and implement those for different CPU generations and different instruction set on Intel architecture, as well as their ARM support with SVE instruction set. There are certain optimizations related to the memory, minimizing the memory access, utilizing caches, and using clever prefetching. New instructions and new CPU platforms and architectures are supported in oneDAL before official hardware launches. So at the time then hardware is released, new things are usually supported. And lastly, there is scale-out optimizations and algorithms that can run in distributed mode, scaling to their thousands of the nodes and solving even larger machine learning problems. It's important to note that not only their particular algorithms are accelerated, but entire pipelines of their high-level applications are accelerated as well. There is imbalanced learn library and the problem that have been solved with different methods using stock scikit-learn version as well as NVIDIA QML implementation and scikit-learn Intel extension on CPUs. And as you can see on this graph, their speedups achieved with the scikit-learn extensions brings the performance on par with their QML, outperforming stock significantly. There are more details through the link on the paper on their why pay more for machine learning. This is one of the examples of the end-to-end applications accelerated with the scikit-learn extension and oneDAL underneath. One of their achievements through the last year in oneDAL is Fujitsu contribution on ARM support. With the additional backends such as OpenBLAS and some open source kernel implemented for random number generation and VSL, we now can compile oneDAL for ARM platform. And this enables full stack, including scikit-learn extension, to accelerate over stock version, achieving noticeable performance improvements, showing that oneDAL and scikit-learn extension are applicable for a variety of the different platforms. For our plans in the future, there is active work on improving open source contribution process and governance for library to simplify process for external contributors. As part of this, we are moving the larger portion of validation and testing to the public, so it will be possible to look on the results and ensure that changes and contributions are of the high quality. Another noticeable change visible from the public would be the merge of the oneDAL and scikit-learn extension products to their same repo, and this would unify things for their end users and contributors to oneDAL project.
Hello, my name is Maria Kranyuk. I'm software engineer from Intel, and I'm one of architecture maintainers of oneMKL interfaces project. And today I'm going to provide short update about this project. So let's start with introduction. oneMK interfaces project attempts to solve a portability problem across different hardware by implementing SQL-based APIs that's defined as part of oneMK specification. So as part of this project, we have a dispatcher between different backends, and each backend it's a SQL wrapper around existing third-party library. So right now we have support for dense and sparse linear algebra, random number generators, and discrete Fourier transforms, supported on x86 CPU, Intel GPUs, NVIDIA GPUs, and AMD GPUs, implemented via third-party libraries such as NVIDIA, cuBLAS, Intel oneMK, and so on. This project can be extended with other hardware targets via other third-party libraries, and at this moment we have around 45 contributors from different teams. So you can find our open source repo on the GitHub. We also have oneMKL group in UXL Foundation Slack channel. On the next slide, I will talk about recent updates in oneMK interfaces project. During this year, we introduced sparse BLAS domain with support on x86 CPU and Intel GPUs that implemented with Intel oneMKL product. We also switched from sparse BLAS 1.xspec API to the newer API from the latest spec that is more compatible with libraries from AMD and NVIDIA, so it will be easier for us to enable other backends for AMD and NVIDIA hardware. We also introduced header-based random number generators device API support, and we also added port FFT backend support. The latest available release for the project 0.5. As for the next year plans, we are working on enabling generic target support, and actually we already have one PR open for enabling BLAS domain via port BLAS backend, which is SQL pure implementation. We also plan to work on sparse BLAS support and support to NVIDIA GPU support via cuSparse and AMD GPU support with RockSparse library. We also have some work in progress on vector mask domain for this project. So first step will be enabling x86 CPU and Intel GPU with Intel oneMKL product, but we also plan to add some referencing for other hardware vendors. And we also have one RFC right now in progress for oneMKL interface project migration to UXL, and also for renaming of the project, so it will conflict with Intel oneMKL product. On this slide, I want to talk about contributing to oneMKL interfaces. So we just recently improved our contributing guidelines, so you can follow it, check the information there. So the project is open for any contributions, could be new backend enabling, or it's also good improvements for existing backend implementations, tests, documentation, or infrastructure. We also have a list of issues and feature requests open. If you wish to contribute to one of them, check the label Help Wanted. So this is the open feature requests and issues waiting for some contribution. If there's any significant changes required, then to follow request for comment process. You can find more information about this process, special RFCs branch oneMKL project. And last but not least, I want to talk about projects that use oneMKL interfaces right now. So the first is Atlas Experiment project, and we actually have individual contributor from Lawrence Bakery National Lab who enabled NVIDIA Courant support our project, and he was motivated by the idea of using RNG domain in Atlas Experiment project for better performance portability across hardware from different vendors. For the next two projects, it's Chromax and NWChem. Hotplay team integrated FFT domain support in these two projects to demonstrate lower maintenance alternatives on NVIDIA, Intel, and AMD hardware instead of supporting three different third-party libraries, obviously three different code implementations. And the last Stack A2 benchmark from Stack Research. So here, RNG domain from our oneMKL interfaces project was on Greek algorithm for getting some performance benefits.
Hello, I'm Timmy Smith, and today I'm going to give an update on the oneDPL project. oneDPL is a high productivity C++ library that aims to minimize programming efforts for parallel application development. Its SQL, OpenMP, and 1TBB backends enable parallel execution on CPUs, GPUs, and other accelerators. If you'd like to contact oneDPL developers, you can start a discussion or open an issue on the repository, or reach out to us on Slack. To learn more about oneDPL, you can check out our online documentation. We also have our project policy documents maintained in the repository. oneDPL has several components. We have parallel algorithms and parallel range algorithms. These algorithms accept execution policies that specify not only how an algorithm is going to run, but on which device it will run. And that's because these execution policies maintain information about the cycle queue that a particular device is associated. The dynamic device selection APIs allow you to offload work to one of several devices, and the particular device that is assigned to execute a piece of work that's been submitted depends on the selection policy that you've specified as well. So our additional APIs, we have iterators like transform iterator and counting iterator that make it a bit easier to work with data. We have C++ APIs that we've tested to confirm that they can be used within your kernels. We also have random number generation APIs that can simplify random data generation. Some projects that use oneDPL include Intel's oneAPI DP++ compiler. The compiler provides a flag, sickle PSTL offload, that will take calls to your standard library algorithms that have received execution policies and replace that with calls to oneDPL with the oneDPL execution policies so that the work of that algorithm is offloaded to a device. In the HPC domain, we have projects like NAMD, Amber, and Hyper, HarborX, Cocos, and Amrex. We also have projects that span a number of other domains as well. Let me talk a little bit about what's happened in oneDPL in the last year. Big focus has been on the improved performance of oneDPL's algorithms. Additionally, the range-based algorithm APIs that we have now as full features of oneDPL were previously experimental. We've also introduced histogram, conditional transform, and sort by key algorithms. To find the latest oneDPL release and the release notes that will explain what's in it, you can visit the releases page of the oneDPL repository. Our current plans for the coming year include introducing additional range-based APIs, improving our asynchronous algorithm APIs, and continuing to improve the performance of oneDPL's components. We do welcome input from the community. We have several specification proposals at the UXL Foundation's oneAPI spec repository that we would greatly appreciate feedback on. If you have an idea for an RFC for oneDPL, you can open that as a discussion or as a PR at the repository. If you're looking to contribute to oneDPL, you can check out the contribution process that we've defined at the repository. Areas where we would especially like to see contributions from the community include new examples using oneDPL, implementation of forward iterator support for our CPU backend. We have some additional ideas for improvements to our OpenMP backend. For those that are interested in testing, improving the input size coverage of our tests is something we'd like to see. If you have an idea for a new backend or a new accelerator or new parallel algorithms, we'd love to see those as well. Something that we're really interested in seeing is community testing on additional hardware types of all of our backends so that we can see oneDPL exercised more fully across the range of hardware that's available to the community. And that's the update that I have for you today. Thank you for your time.
Hi, I'm Mike Voss, and I'm going to be giving an overview and update on oneTBB, oneAPI threading building blocks. oneTBB is a portable C++ library for parallel programming on CPUs. If you're familiar with threading building blocks, oneTBB is the current and modern version of TBB. oneTBB is available as an open source project at GitHub at the URL at the top of the slide, and is also available as a commercially supported product by Intel. It's available for Linux, macOS, Windows, Android, and more, and we support a number of hardware platforms such as x86, ARM, MIPS, and others. Some of the support is done by Intel and others by members of the TBB community. oneTBB has been applied across a range of domains and applications. It's part of the UXL Foundation because oneTBB is a backend for many oneAPI libraries, such as oneDNN, oneDPL. It's available as a backend for oneMKL, and it's also a target when you select the CPU, you execute on top of OpenCL, and OpenCL, or the host, is implemented on top of oneTBB. Our users also have used it directly, oneTBB, in a number of domains such as AI and automation, visual effects and animation, video games, high energy physics, financial applications, medical applications, and many more. You can roughly break down the components of TBB into two large groups. There are parallel execution interfaces. These include our generic parallel patterns like parallel for, parallel reduce, parallel scan, parallel pipeline, as well as the flow graph, which is used for expressing data flow and dependency graphs. All of these high-level execution interfaces are implemented on top of lower-level interfaces, such as tasks, task arenas, and global control. These are also available directly to developers. Task arenas and global control give users performance hooks that allow them to configure and control the performance and behavior of the TBB tasks and TBB task scheduler. In addition to the parallel execution interfaces, there are interfaces that are independent of the execution model. These include a number of concurrent containers like hash tables, maps, queues, and vectors, as well as a widely used scalable memory allocator, and lower level primitives and utilities such as synchronization primitives and thread local storage that are useful when developers need to implement their own algorithms and containers. The reason why TBB is a part of the UXL Foundation is because of its unique place in the ecosystem. TBB is all about simplifying multi-core programming for CPUs. It provides these high-level algorithms and data flow and dependency graphs that I've described, as well as concurrent containers, but also provides a highly tuned task-based scheduler. And the primary selling point for users that choose TBB is that this task scheduler can act as a singleton thread pool, provide composable parallelism that avoids oversubscription. So you can write an application that uses TBB directly, uses third-party libraries that are implemented on top of TBB, as well as use models such as SYCL that when targeting the host use TBB indirectly, and rest assured that the oneTBB library is effectively mapping those tasks from all of those sources onto that singleton thread pool to provide good scalable performance. I like to think of TBB as analogous to level 0, where level 0 is the backend for accelerator offload. oneTBB is the backend for launching parallel tasks onto CPUs. I'd like to take a minute now to talk a little bit about what we've been doing recently within the library and our future plans. So recently we've added a preview feature in the flow graph for try, put, and wait, which allows developers to wait on specific messages as they flow through a graph, whereas before you would have to wait on all activity in the graph. So if you were overlapping messages, there was no easy way to wait for a single message to complete. We also continuously look at improving the scalability of our algorithms and the scheduler, and this year in particular, we made a lot of progress in improving scalability for high core count architectures in task group, parallel for each, flow graph, and the TBB scheduler itself. Our future plans include additional extensions for the high-level APIs with several RFCs in progress. We have a task API extension, which includes improved support for dynamic task graphs, as well as more easily expressing recursive algorithms. We also will continue to work on the preview feature, try, put, and wait, adding support for more flow graph nodes. And we have just begun discussions and around the design for simplified NUMA support in the library. And as always, as new hardware platforms are introduced, we are continuously looking to improve the scalability and performance of existing algorithms in the scheduler. We welcome contributions to TBB. The URL for the GitHub repo is at the top of this slide again. In the repo, you can find a clearly defined process for contributions. We've started a recently new RFCs process for larger design discussions and proposals. We're building a list of desired contributions that we're looking for a collaboration on. One of those I just want to call out is our WebAssembly support in TBB. We do have support for WASM in oneTBB, but there are some known issues and we would welcome contributions in addressing those. And of course, additional platform support for other hardware platforms is always welcome in the repository. If you want to learn more about TBB, you can visit our GitHub repo where there's links to documentation, descriptions of how to contribute all the processes that I've described above, or you can look at the ProTBB C++ parallel programming with threading building blocks that is freely available from APRESS. I look forward to seeing you in the GitHub discussions and participating in the RFCs process, and I thank you for your attention.
Welcome everybody. I'm going to talk about oneCCL, the oneAPI Collective Communication Library. My name is Maria Garzaran. I am a Senior Principal Engineer at Intel, and I am also the oneCCL architect. oneCCL, the Collective Communication Library, provides optimized communication patterns that are used in deep learning frameworks, and we support both CPUs and GPUs. You can see the architecture of the oneCCL on the right. So you can see that oneCCL builds on top of lower middleware for communication, and in particular, we can use two different transports, either MPI or OFI. This allows us to use a large variety of interconnects. We support Ethernet, InfiniBand, HPE Slingshot, and the majority of the fabrics for which we have Leap Fabric. In order to communicate with the GPU, we have two different paths. We have one path which is level 0, which is the low-level communication for the Intel GPUs. And recently, we have added a new path that goes through SQL. Even on the SQL path, we still need to use level 0 facilities because we need to do topology discovery. And we also use level 0, for instance, to be able to access memory allocations that are done by a different process. oneCCL is both an open source project, but is also a commercially supported project. oneCCL is integrated with the frameworks. You can see on the right the picture of how that is integrated. So oneCCL is integrated with Torch Distributed. That is done through the oneCCL bindings for PyTorch. Usually that is known as Torch CCL. It's also integrated with Horobot. That is done with Intel optimizations for Horobot. And so they underneath are calling the oneCCL library. And of course, we support also all the communication patterns that are needed by DeepSpeed. So what have been doing on oneCCL? So we've been adding new APIs. In particular, we have added support for AllGather. We had already support for AllGather B, but we have added AllGather. So in AllGather, basically the idea is that all the processes contribute the same amount of data. We had added also support for the group APIs. Group APIs are group star and group end, and they are used basically to avoid hot synchronization. For now, we only support that for point-to-point operations. We have also added a new flavor for broadcast, where we have send and receive buffer. So the only difference really is on the root node, where basically the data is copied from the send to the receive buffers. For the other ranks, it's basically the same thing. I will be updating soon the specification, so just pay attention to that. oneCCL is running on large supercomputers, and in particular, it runs on Aurora, which is the Argonne National Lab. And so we've been doing optimizations, and they've been using oneCCL to run at a very large scale, 3,000 nodes or more. We have also been working on performance improvements, and in particular, we have significantly improved all reduce, AllGather, and reduce scatter collect. If you want to access the latest release, you have here the website where you can find that. This right now doesn't include the latest updates, but we will be updating the repository very soon. So what is next? What are our plans? So we are preparing, we did actually a presentation recently on the UXL. We are preparing an RFC because we would like to align the oneCCL APIs with other vendor APIs. The reason for that is that, as I mentioned before, oneCCL is integrated with the frameworks, and if we have APIs that are similar, it makes it easier, the integration and upstreaming to the open source. So we are collecting feedback, and so we would like to hear about that. So we will be submitting very soon an RFC. Right now, if you want to see a preview, it's just a pull request, but we will be merging that very soon. So please be on the lookout, because we would like to hear your feedback. So we are also going to continue extending the group API. As I mentioned before, we only support the point-to-point, but we want to add support for collective operations and communicator creation. So we are going to work very closely with the applications to prioritize this support. Right now, oneCCL support one process opens a single GPU, but we are working to add support so that a single process can also open multiple devices. So this is work that we are doing right now. As I mentioned before, we do have a path that is using SQL, and that allows us to basically leverage all the optimizations that are coming in SQL. And in particular, we are working on supporting SQL graph. So the SQL graph allows the user to define a set of compute kernels and communication kernels and express their dependencies. And then we can batch them together and submit the graph. And if that graph is running a loop, basically you can submit that graph multiple times. And obviously we are working on performance improvements that we continuously do that. OneCCL has a defined process for contributions, and you can also submit issues through the link that you have here. We are working on a new template that will be added soon so that it will simplify reporting. We welcome contributions, and we will be willing to collaborate with anyone that want to work with us. This is basically all I have, so thank you very much.